Hello and hi everyone. So my name is Nuring Iwan Natasha binti Muhammad Rizwan and I will be the first presenter for today. And our topic is the least square solution and QR factorization using Gram-Smith process. With the system of linear equation written in matrix form such as AX equals to B. In many real life and mathematical applications, not all system of linear solution has exact solution. So this usually happens when the number of equation is greater than the unknowns. And this such of system is called overdetermined system. So in this problem, we have given the A matrix and also the vector B. As we can see here, the A matrix is 4 by 3 matrix, which is it has 4 equation and 3 unknowns. And because of this, the system of AX equals to B does not has an exact solution because the number of equation is greater than the unknown. Why is this square method? Okay, since the exact solution does not exist and we apply the least square method. The idea of the least square method to find the vector x that minimize the error between AX and B. And this method allowed us to find the best approximate solution of the system. So next, I introduce to you the Gram-Smith process. Okay, the Gram-Smith process is the process that used to convert a linear independence vector into orthogonal and orthonormal set of vectors. So in this presentation, we apply the Gram-Smith process to the column of matrix A. This step is very important because QR factorization allows us to solve the least square problem more efficiently and accurately. For solving the least square problems, we introduce the method known as QR factorization. QR factorization is a technique that used to decompose a matrix A into product of two matrices, which is A equals to QR, where the Q is the matrix with orthonormal column and R is the upper triangular matrix. This factorization is especially useful in numerical methods because it provides a stable and efficient way to solve the least square problem. The objective of our presentation is to apply the Gram-Smith process to the column of matrix A. Next is to construct the orthogonal and orthonormal basis. Next is to obtain the QR factorization of matrix A, and also to use QR factorization to solve the least square problem. And the last one is to verify the solution using mathematical.
Hello everyone, so in this part, I will show you guys how to use least square method. So we are given the matrix A and also the vector B. As you can see, the system has more equation than the unknowns. An exact solution does not exist. You cannot use the exact solution. So therefore, we will apply the least square method using normal equation, which is we will use this formula. And first, we will compute the A transpose multiply by A, and we will get this value. Next, we compute the A transpose multiply by B, and we will get this value. And then, when we will get the value, we will rearrange, follow the formula, and then we will get like this. The x here, we will write x1, x2, and also x3. And then we will compute and get this one. Now I will explain the row echelon approach or Gauss elimination used to solve the normal equation. First we write the augmented matrix like this. And then next we perform row operation to convert the matrix into row echelon form. And then we start by making the first pivot equals to 1. Then eliminate the entries below using elementary row operation. After that, we use the second pivot to eliminate the remaining entries below it, ensuring that each leading coefficient appears to the right of the one above. This process continues until the matrix is in row echelon form. Once the row echelon form is obtained, we apply the back substitution to find the value of x3, x2, and also x1. The calculation I show you here is shown how it been calculated until we will get the echelon from here, and then we will use the back substitution to calculate the value x1, x2, and also x3.
Good day everyone, my name is Nazilawati binti Zikri. In this part, I will explain how to obtain an orthogonal basis and autonomous basis for the column space of matrix A using the Gram-Schmidt process. Okay, we are given the matrix of A, which is matrix A equal to 269, 786, 453, 387. Okay, since matrix A has 4 rows and 3 columns, it is a 4x3 matrix. Okay, for column space and span, okay, let the column of A be denoted as V1 equal to 2743, V2 equal to 6858, V3 equal to 9637. Okay, then the column space of A can be written as column of A equal to span of set V1, V2, V3. Okay, this means that every vector in the column space of A can be expressed as linear combination of these 3 vectors. Okay, next we perform elementary row operation on matrix A. This is how we perform ERO. After reducing A into reduced row echelon forms, we obtain this matrix which are 100, 010, 001, 000. From this result, we observe that there are 3 pivot columns. The rank of A is 3. The column of A are linearly independent. Okay, since A has 3 linearly independent columns, the column space of A has dimension 3. Therefore, the column of A span a 3-dimension subspace of R4. Okay, to construct an orthogonal and autonomous basis for the column space of A, we apply the Gram-Schmidt process. Okay, the Gram-Schmidt process converts a linearly independent set of vectors into an orthogonal set and then into an autonomous set while preserving the same spans. Okay, we start by defining the first vector. Okay, let U1 equal to V1 equal to matrix of 2743. Okay, we start by defining the first vector. Okay, let U1 equal to V1 equal to matrix of 2743. Okay, to find the second orthogonal vector, we subtract from V2 its projection onto U1. Okay, the formula for projection is V2 equal to U2 minus bracket V1 multiply U2 over V1 multiply V1 close bracket multiply with V1. After computing the dot product, we obtain for U2 which is matrix of 122 over 39, negative 80 over 39, negative 29 over 39, and 48 over 30. Okay, this vector is orthogonal to U1. Okay, next we compute the third orthogonal vector by subtracting the projections onto both previous vector. Okay, for formula V3 equal to U3 minus bracket of V1 multiply with U3 over V1 multiply V1 close bracket V1 minus bracket V2 minus U3 over V2 multiply with V2 close bracket multiply with V2. Okay, after performing the calculations, we obtain for U3 or V3 which is matrix of 2.23475, 0.52639, negative of negative 0.72793 and negative 1.74749. This vector is orthogonal to both U1 and U2. At this point, we have obtained the set of U1, U2, U3, which satisfy the following. which is the vector are mutually orthogonal. Each vector lies in the column space of A. Together they span the same space as the column of A. Therefore, set of U1, U2, U3 is an orthogonal basis for the column space of A. Okay, to obtain an orthonormal basis, we normalize each orthonormal vector. The norm for V1 equal to square root of 78. The norm of V2 equal to square root of 1099 over 39. The norm of V3 equal to square root of 8.85 for 80. Now we define for W. Okay, we use this formula for W1 equal to U1 over the norm of U1. W2 equal to U2 over the norm of U2. W3 equal to U3 over the norm of U3. Okay, which give the answer for W1 is W1 equal to matrix of 0.22646, 0.79259, 0.45291, 0.33968. Okay, for W2, matrix of 0.54099, negative 0.38642, negative 0.14008, 0.69555. Okay, for W3, equal to matrix of 0.75100, 0.17690, 0.24462, and negative 0.58725. Okay, in conclusions, using the Gram-Schmidt process, we successfully transformed the linearly independent column of matrix A into an orthogonal set and then into an orthonormal set. Therefore, the set of U1, U2, U3 is an orthogonal basis for the column space of A. The set of W1, W2, W3 is an orthonormal basis for the column space of A. Okay, this orthonormal vector will later be used to construct the Q matrix in QR factorization, which is essential for solving the least square problems. Okay, here I have attached the complete step-by-step solution for your reference. That's conclude my part, and I will now hand over to the next presenter. Thank you.
Assalamualaikum and good day. My name is Nurul Anis Husna binti Zulkifli. Next, I will explain on how to solve a system of linear equations AX equals to B using QR factorization. This method is especially useful for solving overdetermined systems and avoids computing matrix inverse, which improves numerical stability. In the question, we are given the matrix A is equal to 269, 786, 453, 387, and the vector B is equal to 7682. Our objective is to find the vector X that satisfies AX is equal to B. Using QR factorization, matrix A is decomposed as A is equal to QR, where Q is an orthonormal matrix and R is an upper triangular matrix. From the calculation using Gram-Schmidt process, the matrix Q is obtained as Q is equal to 0.22646, 0.54099, 0.75100, 0.79259, negative 0.38642, 0.17690, 0.45291, negative 0.14008, negative 0.24462, 0.33968, 0.69555, and negative 0.58725. After obtaining the orthonormal matrix Q, we complete matrix R. Matrix R is obtained using the formula R is equal to Q transpose A. Since the columns of Q are orthonormal, multiplying Q transpose with A produces an upper triangular matrix. After performing the matrix multiplication, we obtain R is equal to 8.83173, 12.68147, 10.53017, 0, 5.01858, 6.99900, 0, 0, and 2.97579. Because all diagonal elements of R are non-zero, matrix R is invertible and the system has a unique solution. After that, we substitute A is equal to QR into the equation AX is equal to B. We obtain QRX is equal to B. Next, we multiply both sides by Q transpose. We will get Q transpose QRX is equal to Q transpose B. Since Q transpose Q is equal to identity, this simplifies to Rx is equal to Q transpose B. After performing the matrix multiplication for Q transpose B, we obtain Q transpose B is equal to 10.64340, 1.73887, and 3.18694. Next, based on the matrix R that we obtained just now, the matrix R is an upper triangular matrix given by R is equal to 8.83173, 12.68147, 10.53017, 0, 5.01858, 6.99900, 0, and 2.97579. Since R is an upper triangular matrix, we solve the system using back substitution. Starting from the third equation, 2.975798 is equal to 3.18694, and we will get x3 is equal to 1.07096. Next, we substitute x3 into the second equation. We will get x2 is equal to negative 1.10847. Finally, we substitute both x2 and x3 into the first equation, and we will get x1 is equal to 1.51987. Therefore, the solution to the system is 1.51987, negative 1.10847, and 1.07096. In conclusion, QR factorization allows us to solve the system efficiently without computing matrix inverse. By transforming the system into an upper triangular form, we can easily apply back substitution to obtain the solution. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurauni Nadira and I will be explaining the mathematical verification part. And first, after all of the hand calculation, we can check and we can verify all of the answers by using Wolfram Mathematica. So I'm going to show you how we use the Wolfram Mathematica to solve all of the questions. So first, as the input, we need to define the 4x3 matrix and 4x1 vector B. As you can see here, we have matrix A and vector B. And then for the second step, we have to extract columns for Gram-Schmidt, which is A1, A2, and A3. And then for the third step, we use Gram-Schmidt process to find orthogonal basis, and then we use the same process to find orthonormal basis. And for the last step, this is where we use Wolfram Mathematica to solve for x. So after we put all of the inputs, and then we need to press shift enter to have the output for the results. So as we can see here, we have the orthogonal basis vectors result, which is A1, and orthonormal basis columns of Q, which is question A2, and then numerical solution of x, which is question B. As we get the output same with the hand calculation answers, so we can say that the solution by hand and by Wolfram Mathematica is verified. Therefore, Mathematica verifies that the least squares solution obtained by using QR factorization and the Gram-Schmidt process is correct. So, as in conclusion, we can conclude that the least squares solution can be efficiently obtained by using QR factorization derived from the Gram-Schmidt process by using hand calculation, and also the results can be verified by using Wolfram Mathematica.
Next, regarding efficiency, the Gauss-Seidel method is considered more efficient than the Jacobi method. Although both methods require a similar number of arithmetic operations in each iteration, the key difference lies in the total number of iterations needed to reach convergence. Since the Gauss-Seidel method converges more rapidly, it reduces the overall computational effort. Therefore, for large systems of linear equations, where computational cost and time are important considerations, the Gauss-Seidel method is generally more suitable and practical. Lastly, in terms of accuracy, both the Jacobi and Gauss-Seidel methods are capable of producing accurate solutions, provided that the convergence conditions are satisfied. When both methods converge, they tend to approach the same numerical solution. However, the Gauss-Seidel method achieves the desired level of accuracy in fewer iterations compared to the Jacobi method. This makes Gauss-Seidel more practical in real-world numerical computations, especially when high accuracy is required within a limited number of iterations.